Hello, my name is Jeppe Byskov. I'm the director of the Industrial 3D Printing Center at the Danish Technological Institute. In this course, myself and a number of my colleagues, all of which are additive manufacturing experts, will give you an introduction to additive manufacturing as a manufacturing technology.
Hi, my name is Henning. In this first video, I will go through the history of 3D print. The agenda for this video is that we first look at the first inventions that were the plastic printers. Then we look at the 90s and onwards, where the metal printers were introduced and some other technologies. Then we look at the current situation, and finally we look at where is it all heading. We start by looking at the first inventions. It started back in 1980 in Japan, where Dr. Hideo Kodama filed a patent on photopolymer curing using UV light. However, that invention was never commercialized. Then, a few years later, in US, Charles Hull filed a patent for stereolithography. And in 1986 he started the company 3D Systems, which is still on the market, one of the big players. And then in 1988, the first commercial rapid prototyping printer, SLA1, came on the market. Then the next technology that was invented was the powder bed fusion of plastic. In 1986, Carl Deckert from the University of Texas filed a patent on the SLS technology. This was commercialized in 1992, where DTM launched a beta machine. And in 1989, the European company EOS was founded, and it's still one of the big players on the market. The third well-known technology is FDM, fused deposition modeling, the extrusion technology, where we also today find all the cheap printers. In 1989, Scott and Lysacrom filed a patent for FDM, and Stratasys was founded, and that's still one of the big players on the market today. The first commercial machine was shipped back in 1992. When the patent expired in 2009, they lived for 20 years, we saw an explosive growth of FDM machines, and the prices dropped from around $10,000 per machine to under $1,000 per machine. In the 90s, a lot of things happened. Only few machines were installed, and there were limited commercial success on machine sales. However, there were a lot of R&D activities, and several new technologies were invented. The situation was that there were 3 times more patents filed than machines installed, and that led to a huge number of patent fights where the companies, they tried to defend their rights. Also in that decade, metal AM technologies were developed and commercialized. When the first patents expired around 2010, the exponential market growth really took off. That can be seen also on the graph below. Then we look at the 90s and onwards, and what happened there. One of the technologies that came up in the 90s, at the beginning of the 90s, was laminated object manufacturing, LOM. That is lamination of sheets that were bonded together and cut into shape. It could be either paper sheets or metal sheets, but that turned out never to be a great success commercially. Binder jetting is a successful technology also today, where you glue powder together of different materials, and for metal subsequently you have to sinter the parts. In 1996, C Corp made a gypsum powder printer where the powder was glued together using MIT's inkjet technology. And in 1999, Extrude, now X1, made the first metal binder jetting machine. And finally in 2016, Hewlett Packard introduced the multi-jet fusion machine for plastic powder. One of the metal technologies invented in the 90s was DED, directed energy deposition, where you place powder, and where you place the powder you also at the same time melt it using an energy source. The first machine with this principle was launched in 1997 by the company Aeromet, where they produced the world's first laser additive manufacturing machine for titanium powder. In 2014, Skiaki, they made a machine that melted the powder using an electron beam. Also in the 2010s, several systems called wire arc additive manufacturing were built. In principle, they are just welding machines where the welding head is moved around by a robotic arm, and by doing that they print parts in 3D. Powder bed fusion is the most widespread metal print method today. The first system based on this principle was launched in 1999, where Voeckle and Schwarze in Germany, they introduced a steel powder machine that used a laser to melt the powder. It's also called SLM, a name that is still on the market today. In 2003, Arcam in Sweden launched their first machine where the powder is melted by an electron beam. Material jetting is basically an inkjet printer where you, instead of ink, just print with materials. So you can print multicolor and you can mix different photopolymer materials. The first machine of this kind saw the light on the market in 2001 and was launched by Objet Geometries in Israel, now taken over by Stratasys. And again, that photopolymerization, the technology where it all started, a couple of new curing technologies have come up later. In 2002, EnvisionTEC came up with their first machine, the Perfactory resin printer. They use the DLP mirror chip known from projectors to cure the resin. And in 2015, Carbon 3D, they came with their principle called the CLIP technology, where they cure the resin with an LED matrix and thereby curing a full area or frame at the same time. Where are we today? Well, first of all, here you see an overview of all the technologies that we have just been through. They are classified in 7 different groups, and with green is indicated the year when the first machine of each technology was launched. In this overview from AMFG, we show the additive manufacturing landscape as per 2020. What we see here is that there are a lot of players in the market. There are 3D printer manufacturers, both for professional equipment and for hobby or desktop machines. There are software vendors and material suppliers, and also post-processing equipment manufacturers. Finally, we will see where is it all heading. Regarding machine sales, globally we see an exponential growth, both for industrial systems, defined as the one with a price tag above $5,000, and for desktop printers and hobby printers with a price tag below $5,000. Regarding materials, we see there's on a continuous basis materials being developed for almost each technology. We also see that the material prices decline because of increased competition and more vendors come up, also vendors independent of the technology suppliers. In 2020, still almost 80% of all materials were plastic materials, almost 20% of all materials were metal materials, and the remaining part count, for instance, ceramics, around 2%. For all materials, we also see an exponential growth as for the machines. That's shown on the curve to the right. Overall, we see for additive manufacturing a clear trend from prototyping towards real manufacturing and series production. That means we still produce prototypes, but more and more we produce tools, molds, fixtures, robot grippers and end-use parts, and there is a tendency towards series production rather than individual parts. Also, we see a clear consolidation trend in the additive manufacturing industry, where companies are merged or taken over, and it's going towards fewer but bigger companies. In 2020, globally, around 1 per mil of all production were additively manufactured. Some people find that this may grow to 5% in the future, so there's still a huge growth potential.
Hi, my name is Christopher, and in this module you will get an introduction to the 7 main AM technologies. Let's have a look at the agenda for this module. First, we will look at an overview of the most common additive manufacturing technologies. We'll go through a 4-slide introduction for each basic technology that is going to cover the technology itself, the materials, the pros and cons of the technology, and the leading machine manufacturers. Then finally, we will have a look at the technology maturity and industrial landscape. Here we have an overview of the 7 general technologies. First, we have vat photopolymerization, also known as VAT. Then we have material extrusion, material jetting, binder jetting, powder bed fusion, direct energy deposition, and sheet lamination. We'll be going through each of the subcategories of these 7 general technologies. First, we have the VAT technology. The VAT technology originated with the SLA process, also known as stereolithography. The process works by having a UV light curable resin in a bath. A laser source is applied to the resin and cures the resin locally. This is done layer by layer, as we can see here in the following video. We first fill up our resin, and we then apply our laser layer by layer, slowly building up our part one section at a time. The DLP process, or digital light processing, is very similar. However, we are using a projected UV light instead of a laser. This means that we can process an entire layer at a time, and the process is typically faster. CDLP, or continuous digital light processing, is similar to DLP. However, the process platform is continuously moving, and we build our part as we go. The VAT technology utilizes a range of materials. You can print everything from elastomers to transparent material, and also for dental applications. Here we have an overview of the pros and cons of the VAT process. The pros include good for prototyping, it is quick to print, and you can obtain a surface finish all the way down to 10 microns. Some of the cons include the parts being brittle, and since they're reacting to UV light, they will react to sunlight, and that leads to a loss of mechanical properties. Then there is also extensive post-processing required. Let's have a look at the leading machine manufacturers for the VAT process. For SLA, we have Formlabs 3D Systems and DWS. For DLP, we have B9 Creations, SprintRay, and for CDLP, we have Carbon and EnvisionTech. Now we will move on to the material extrusion process. The material extrusion technology is most well known with the FDM method, or fuse deposition modeling. The way it works is that you have a polymer material on a material spool. The material is extruded through a heated nozzle and deposited on top of your build platform. Layer by layer, you will be building your object. There are typically 4 configurations. The first and most well known is the Cartesian 3D printer. As we can see here on the short video, we have a build platform that can elevate in the Z direction, and we have a nozzle that can move in the X and Y direction. We can then slowly build up our part like this. Then we have the Polar 3D printer. Here the platform moves while the nozzle is steady. The third configuration is the Delta 3D printer. Here the nozzle is being controlled using 3 linear actuators, and the material is being deposited on a steady platform. The final configuration is the Robot Arm 3D printer. Here you are simply using a robot arm to control the deposition of the material as it is being extruded through the nozzle. Let's have a look at the materials used for material extrusion. We have here divided it into commodity materials and engineering materials. The main commodity materials include PLA, which is easy to post-process and has good heat resistance. Then we have ABS, which is known for great stiffness and durability and a variety of colors. For the engineering materials, we have Onyx FRA. Here we can use carbon reinforced nylon, which is flame retardant. We also have Fibrex nylon with, in this case, 30% of glass fiber. This is simply glass reinforced nylon that has excellent mechanical and thermal properties. Let's have a look at the pros and cons of the material extrusion technology. The pros include the technology being cheap. It is great for prototypes, and it is great for beginners. Some of the cons include support being required in some cases. The properties are anisotropic, and you will obtain a poor surface finish. The leading machine manufacturers within material extrusion includes Stratasys, Ultimaker, Markforged, and MakerBot. Let's have a look at the material jetting technology. The material jetting technology can be divided into 3 sub-technologies. First being MJ, or material jetting itself. This is the main industrial technology. Then we have NPJ, or nanoparticle jetting. This is using particle-infused liquid and heat to evaporate the liquid. Then we have DOD, which is drop on demand. It uses 2 print jets, one for building material and one for support material. The technology works similar for all 3 cases, and we here have a video demonstrating how the material jetting technology works by depositing material and using a UV light to cure the material as we go. Let's have a look at the available materials. Here we have a view of the PolyJet materials, and that is Stratasys' version of the material jetting technology. We can see that there is a wide range of polymer materials, all the way from 2003, where they developed a rigid material called RGD 720. Through the years, they have developed different kinds of materials. In 2011, they developed a clear material called VeroClear. We can see that after 2016, they have developed a full color realism material. If we have a look at the pros and cons of the material jetting process, we can see that we can obtain a great surface finish. It is considered the most accurate 3D printing technique, with dimensional tolerances going all the way down to 0.02 millimeters. We can also have multi-material combinations. Some of the cons includes that the parts are often brittle, and the material properties are generally not the best. Finally, both the machine and materials are quite expensive. The leading machine manufacturers for material jetting includes, for material jetting, Stratasys and 3D Systems, for nanoparticle jetting, XJet, and for drop-on-demand, SolidScape. Now we will move on and have a look at binder jetting. If you have a look at the binder jetting technology, we can see that it is subdivided into 2 technologies. One being BJ, or binder jetting, and the other being MJF, or multi-jet fusion. If we have a look at the process for the binder jetting technology, we can here see how we are applying a binder to our powder. After having applied the binder, we are heating up the binder to cure it together with the powder particles. After it being cured, we have what we call a green part. The green part then needs to go through a debinding process where we will obtain our brown part. It is very brittle in both of these conditions. Finally, we will move our brown part into a sintering process where we will sinter together our powder particles, obtaining our final geometry. The multi-jet fusion process is very similar to the binder jetting process. However, we are using polymer instead of metals. Here we are in one continuous motion, both applying the fusion agent and heat to fuse together the part. If we have a look at the available materials for the binder jetting technology, we can see that for binder jetting itself, we have a wide range of alloy metals. We can also use ceramics, and we can even use ceramic metal composites. For multi-jet fusion, it is a wide range of polymers that are available. Let's have a look at the pros and cons of the binder jetting process. We have fast production of parts, we can obtain high layer resolution, and the as-built surface finish is all the way down to 6 micron. Some of the cons include, specifically for binder jetting, that the parts are fragile in both green and brown state. The debinding process is highly labor intensive, and the parts will shrink in a non-uniform manner and all the way up to 27%. The leading machine manufacturers within binder jetting are X1 and Digital Metal for metal binder jetting. For ceramic binder jetting, it is 3D Systems and VoxelJet, and for multi-jet fusion, we have HP. Now we will move on to powder bed fusion. The powder bed fusion technology can be subdivided into 3 main categories. SLS, known as selective laser sintering, SLM, known as selective laser melting, and EBM, known as electron beam melting. The principle behind all 3 subcategories are the same. We are either applying a laser or electron beam to a powder bed of powder. The powder can be either polymer, which is used typically for selective laser sintering, or metal, which is used for SLM and EBM. We here have a video showing the SLM process. We can see how we are applying our laser to the powder bed. We do this 1 layer at a time and build up our part. In essence, the technology is very similar to SLS and EBM. Let's have a look at the available materials for the powder bed fusion process. For SLS, we are working with polymers, and we can use everything from PA12 to PA with fillings such as carbon, glass, or metals. For SLM, we work with metals. Here we can use everything from stainless steel to Inconel, aluminum alloys, and even precious metals. The EBM process is very similar, and we can also use stainless steels, titanium alloys, and even alloys such as cobalt chrome. The pros and cons for the powder bed fusion process includes that you can create complex geometries. It is ideal for functional parts. For the SLS technology, you will not require any support. And the SLM and EBM technology both provides great mechanical properties. Some of the cons includes that you will have a grainy surface finish on as-built parts. The feature resolution is not the best. However, SLM is better than EBM, which is better than SLS. And it is also prone to warping in large flat areas, except for EBM, because it is being processed at a very high temperature. For both SLM and EBM systems, there is a big con that they are very expensive. The leading machine manufacturers within powder bed fusion is, for SLS, EOS and 3D Systems. For SLM, we have EOS, Concept Laser, Renishaw, Trumpf, DMG Mori, Prima Additive, and SLM Solutions. For EBM, we have Arcam EBM and Geol. We will now move on to directed energy deposition. Directed energy deposition can be subdivided into three main categories. First being LENS, known as Laser Engineering Net Shape. Then we have EBAM, known as Electron Beam Additive Manufacturing. And then we also have WAM, Wire Arc Additive Manufacturing. The basis of the technology is that you're using either a laser beam or electron beam to melt powder or wire as it is being deposited on a substrate. The wire arc additive manufacturing process is very similar. However, here you are applying a current to your deposition nozzle and substrate, which creates an electric arc between the two, which can melt the material as it is being extruded. If we have a look at the process of the technologies themselves, we can here see how the LENS process works. We are applying our powder together with a laser, allowing us to build up our part. The EBAM process works similarly. However, here we are using a wire to deposit, and we have an electron gun out of view in this video. Finally, we have the WAM process, which is using the wire arc melting to deposit a wire as it is being extruded, and we can see how we can quickly build up a bathtub-like structure. The available materials for directed energy deposition include stainless steels, titanium alloys, Inconel, aluminum alloys, and even copper. If we have a look at the pros and cons of the directed energy deposition process, we can see that you will obtain good mechanical properties. It is cheap compared to other metal AM processes, and it is great for large structures, as well as excellent for repairing. Some of the cons include the obtainable tolerances being relatively poor. It is not ideal for prototyping, and you will have a highly rough surface finish. The leading machine manufacturers within directed energy deposition includes for the LENS technology Optomec, Beam, and Prima Additive. For the EBAM technology, it includes Skiaki, and for WAM, it is Ramlab and MX3D. Now we will look at the final of the 7 main technologies, namely sheet lamination. For sheet lamination, the specific technology is known as laminated object manufacturing, or LOM. The technology works by having a foil supply of either thin metal or paper. A heated roller is being rolled across the foil, ensuring that it is bonded towards the lower part of the object that you are building. Afterwards, a laser is cutting up your piece to ensure that only the area of interest is being left. The process is also possible to use for paper with color, and after having built up your paper part, there are some manual processing removing the layers that are not needed. The most commonly used material for sheet lamination is standard paper, but we can also produce structural parts by using fiber-reinforced sheets or rollable metal sheets. Let's have a look at the pros and cons of the sheet lamination technology. The pros and cons includes that the materials are cheap and the production costs are low. You can create large parts and you don't need any support. However, some of the cons includes that you cannot produce complex geometries, the printers are relatively expensive, and you will only obtain a poor surface quality. The leading machine manufacturers for the sheet lamination technology are originally Helicis and EMCOR. Helicis has since been succeeded by Cubic Technologies, and EMCOR has been acquired by Clean Green 3D. Now we will have a look at the technology maturity and industrial landscape of metal AM and polymer AM. Let's first have a look at the maturity of the AM polymer technologies. All of the technologies that we covered, including VAT, filament-based material extrusion, powder bed fusion, and material jetting, are all in the top right corner, which means that they are used for widespread industrial use or industrially in general. If we have a look at the metal AM maturity index, we can see that the SLM technology has industrial widespread use. The lens technology, EBM technology, and WAM technology have industrial use. And finally, both EBAM and binder jetting are in the category first applications. If we take a look at the metal additive manufacturing technology landscape, we can see that there is a wide range of different technologies not being covered in this module. At DTI, we are focusing on binder jetting and laser powder bed fusion, where we have in-house industrial production using SLM machines. The polymer additive manufacturing landscape is very similar. We can see that there are many more technologies than we have covered in this module. And at DTI, we are focusing on powder bed fusion, where we are using SLS machines for in-house industrial production.
Hi, my name is Anders. In this chapter, we're going to look at the workflow in 3D printing. In this chapter, we're going to look at CAD models and formats that can be used for 3D printing. We're going to look at build preparation and support generation. Then we will cover build simulation of the process. We're going to look at the printing process itself. And finally, we have post-processing. First of all, we need a 3D model of the part that we would like to print. We will make that in some kind of CAD program. For industrial use, you will typically use programs as SolidWorks or CATIA. These programs use parametric modeling, where it is easy to go back and make changes, but also easy to make new changes. Some of the common formats for these programs are either STEP or Parasolid X_T. For non-industrial use, the STL format is common. This is a dead format where it is more difficult to go back and make changes and make new changes. The STL format uses triangles to represent the model. This, however, makes it difficult to make rounded curves. In the future, the 3MF format could replace the STL format and solve some of the issues. If we proceed to the build preparation, it is different for the different technologies. Here we see the 7 main AM technologies. We will focus on some of the differences in the next couple of slides. First, we will look at the build preparation for laser powder bed fusion, FDM and SLA, which is quite similar. First, the CAD model is imported in the job preparation software. This could, for instance, be Materialise Magics. Next, we need to orient our part in the printer. This is typically a compromise between getting high level of details, but also printing as many as possible parts in each build. Finally, the support structure should be applied to the part, which ensure that the part is attached to the platform during the printing. Keep in mind that the support structure should also be easy to remove after the printing. You can find more information about the build preparation at the Materialise Magics website. Next, we will look at build preparation for material jetting and SLS, which is slightly different. Here, parts can be nested in 3 dimensions within the build chamber, and support structure is not needed. When you don't need support structure, you have greater design freedom compared to other print technologies. Just be aware that you should be able to remove powder from channels and cavities after printing. Before printing, you can simulate the whole printing process. You do this to predict and avoid failure during printing, and to estimate geometrical distortion, and you can even use it to compensate for the distortion. Build simulation is often used for laser powder bed fusion and metal binder jetting, but also in some cases for FDM and SLS. After printing, we need post-treatment. Here are some examples of initial post-treatment. For FDM and SLA, you use screwdriver and grippers to remove the support structure. For SLM and E-beam, the two metal technologies, you first need a furnace to remove residual stresses. Then you need an angle grinder or grippers to remove the support structure, which is more difficult to remove compared to FDM and SLA. For SLS and the jetting technologies, we don't have support, but the powder is more difficult to remove. Here we use a compressor to blow away loose powder, and we can also use piano wire to remove powder from internal channels. Finally, we have surface finishing. For metal printing, we use more aggressive technologies. This could be abrasive blasting, where you typically use glass or corundum beads to even out the surface. It could also be deburring, where you use ceramic chips to grind the surface. For polymers, you can also use deburring. Furthermore, you can use chemical etching to seal and smoothen the surface. Finally, you can also color your parts. This is especially relevant for SLS parts. Finally, we have a video showing the entire workflow. In this case, it's laser-powered bed fusion in metals. First, we are preparing the build job by finding the perfect orientation and adding support structure on the part. Next, we are printing the part layer by layer. After printing, we transfer the build cylinder to a powder removal station. Here we remove all the powder that is not used to print the part. After removing the powder, the parts need stress relief. This is typically done in a furnace. After stress relief, the parts are removed from the platform with a bandsaw, and the support structure is removed by hand. Finally, we have surface finishing. Here we use abrasive blasting and deburring.
Hi, my name is Ronnie, and in this module we'll look at some design features that can add value to your 3D printed part. Let's start by looking at the agenda for this module. First, we'll look at why we should design for 3D printing. Then we'll look at some of the features that can add value. And finally, we'll look at 9 different ways where we can generate added value by designing for 3D printing. First, we'll look at how we can get the most value out of our 3D printed parts and the design process behind them. If we start in the bottom of the pyramid, then the 3D printing technology started as a tool for rapid prototyping. Here, we usually have a low volume of parts. The next step is that we go in and replace an existing part with a 3D printed part without changing the design. Here, we get a little bit of added value out of the 3D printing technology. In addition, we can go a further step up, and here we'll look at part consolidation. This is where we go in and take several parts and consolidate them into one part, thereby utilizing the 3D printing technology and adding more value. And if we jump to the tip of the pyramid, then we're in the category of design for 3D printing, where we start to create new products. In this module, we'll focus on the tip of the pyramid, and we'll look at different examples of products that have gained an advantage by being designed specifically for additive manufacturing. I'll quickly go over the 9 overall features, and then afterwards we can go in depth with each of them and look at some cases where these features have been used. If we start in the top left corner, we can see that we can use 3D printing to get some new functionality into our parts. We can also start to make some lattice structures that weren't possible before. We can start to optimize our components towards lightweight, thereby making them both lighter and stiffer. We can begin to make part consolidation, where we put more parts together in one. We can make channels and tube connections that weren't possible before. We can also make mass customized products in large numbers without added expenses. And in addition, we have the possibility of making some components with thermal properties that weren't possible before. The 3D printing technology also gives us a large extent of design freedom that we can utilize. And finally, the computer is one of the really strong tools when designing for 3D printing. So we'll also look at how we can use that. If we start to the left and assume that we need to design a product, well, then we can take the balls from the top row and add them to the basket. Thereby we add some value to this product, which justifies the use of 3D printing. The more balls that we can start to put in this basket, the more value we can add to the product, and the more we can justify using 3D printing as a manufacturing technology. Let's take an example to show how these baskets can be used to design a part. And remember, the more features that we can get into the basket, the better the product we get. So if we take a relatively simple part like this nozzle to make cookies, then it used to be made out of 6 parts, but with 3D printing we can make it in just 1 part. So here we have some part consolidation. Furthermore, the flow through the nozzle is more smooth and even, and we can get that by utilizing some of the possibilities of making special channels. And finally, we can use mass customization, where depending on the cookie that you want, we can quickly change the design of the nozzle so we get a nozzle that fit the individual cookie that you want to make. Now we've taken a brief look at why we should design for 3D printing and how we can utilize these features. Now we'll take a closer look at the 9 different features and see where they make sense by looking at some different cases where they've been used. And what we'll see when we dive into these cases is that a lot of these cases actually utilizes more than one feature. We'll start by looking at part consolidation, which essentially is about reducing 2 parts to 1 part. We can illustrate this with the toolbox to the right, where on the one side we have a toolbox consisting of a lot of bolts and joints, and we can actually reduce that to only 2 parts. And the new toolbox has the same function, only fewer parts. This is interesting because it saves a lot of assembly time, and we don't need to have as many spare parts in stock. Often we can also save some weight, and it reduces the amount of contact areas, which could be of interest to some industries. Here's the first case to illustrate part consolidation, and this is the layout that I'll use for all the cases. So in the top right corner we can see the basket, and we can see the features that we added to the basket in this case. This particular case was about reducing the number of components in the part because there were way too many assemblies and joints. Because of that, the part was hard to clean, and since it's featured in a machine where it's in contact with fresh meat, it needs to be cleaned every day. So the more simple we can make it, the more time we can save on cleaning. Therefore, the design ended up looking like in figure B, where we've taken the 42 component and reduced them to just 1 component. We have no assemblies and we've reduced the weight by 50%. And since the part is moving a lot and really fast, that's an advantage too. And we've done that by 3D printing in titanium. Another case is this robot gripper, which conventionally consists of a lot of parts, as you can see in figure A. In this case, it's approximately 72 parts, and we can make that much more simple by 3D printing it. In fact, we can actually reduce it to only 8 different parts. We have some suction cups, some pneumatics, and then just the gripper itself. Another cool thing about this gripper is that it's actually generated in an online software, so we use computer power to design it, and that way we can design it in just under 10 minutes. Now we'll take a look at how we can design channels and tubes, which weren't possible to design before we had the 3D printing technology. So why are channels an interesting feature for 3D printing? Well, if we look at the first picture, then this is how we make holes conventionally. We drill in different directions to make some channels, and then we plug the holes afterwards to shut off the channels. But if we then look at the next picture, this is how we would do it with 3D printing. And as you can see, it's much more smooth around the edges. So why is this interesting? Well, if we look at the figure below, we can see how the speed of a fluid passing through a channel changes depending on how soft a curve it needs to pass. So if we have a 90-degree turn, then we're at 18.2 meters per second. But if we then optimize the channel, well, then we reduce this by 3 meters per second, and that means that we have less of a pressure drop and we need less energy to push this fluid through the channel. This can be used when we have some fluids, for instance water or oil, that needs to pass through a channel. Here we can then reduce the pressure needed to push the media through the channel, thereby saving energy. So that's why it's interesting to look at these channels. The fact that we can make channels with 3D printing that are curved instead of just straight has been utilized extremely well in this case from the German company SMS Group. This is a spray head for maintenance of large injection mold. It mixes air and lubricant inside this manifold. And if we look at how it was made previously, then we can see in the picture to the left that it was a massive block consisting of a lot of different parts. That means that when we start to look at 3D printing, there's definitely a potential for reducing the weight. If we then compare it to the 3D printed version to the right, we can see that this is much smaller, so there's definitely a weight reduction. We've also optimized the flow, and it's easier to get the lubricant to where you want it because we can control the placement of the nozzles much better. By 3D printing this spray head, it's now possible to print it in metal, but we can also print it in nylon with the powder bed fusion technology, and it can actually withstand the high temperature. In fact, this is such a good idea that SMS Group has chosen to patent this solution because they see a great business opportunity. One of the places where these channels are particularly interesting is in the injection molding industry, where 3D printing allows us to have what we call conformal cooling. If we look at the first picture to the left, then this is how we conventionally made channels, by drilling them all out. Now that we've started 3D printing the channels, then we can make them curved. And conformal cooling is all about getting these channels as close to the surface of the metal block as possible, because then we can cool our plastic part much faster when we cast it. In a minute you'll see a picture of what such an injection mold looks like. But if we look at the cooling effect, then we can see in the picture in the bottom left that the conventional mold has a much higher temperature than in the 3D printed mold. This means that we can actually use the 3D printed mold to produce even more parts than it was previously possible. This is also the focus of the next case, where we'll look a bit more in depth into how this is used in real life. This is an example of how we make a shield for a high pressure cleaner. Previously, as we can see in figure A, all the channels were drilled. This is one way to do it. But now that we can use 3D printing, we can have it look like in figure B. Here we can see that it makes sense to 3D print half of the injection mold. It didn't make sense to print all of it, and that's why we still have some drilled channels. But in fact, this resulted in the cooling time being reduced from 22 seconds to just 10 seconds. So you may think that that's not a lot, but in fact it's 55%, and that means that you can go from producing 1500 parts a day to producing 2100 parts a day. That's an increase of 40% for what the same machine can produce only with a 3D printed injection mold. Next up, we'll look at mass customization, where we can 3D print parts that perfectly fit the individual person. So what is mass customization? Well, this is when we design products that perfectly fit their function. And as the function changes, we can also quickly change the products. This means that we often get some better solutions and that they are often a much better fit. This is really interesting when we look at parts that need to fit the human body. So if, for instance, you needed a custom-fit bike helmet, then you would be able to 3D print it. One of the industries that have really seen an impact from using 3D printing is the hearing aid industry. Towards the end of the 1990s, you went from modeling these hearing aids and then making them by hand to now 3D printing them. The way you make these hearing aids is that you take a wax cast of the person's ear, then you scan it and put it into the computer, and via a preparation program it goes to the 3D printer where it's printed, often on an SLA printer. Then you get the finalized print, you add the electronics, and then the product is ready for the client. This means that you've saved a lot of manual hours in the manufacturing process by 3D printing these hearing aids. So the hearing aid goes outside the body, but using metal 3D printing we can actually start to print parts that go inside the body as well. In this example, it's a hip socket that's being 3D printed. The hip socket consists of two 3D printed parts. In this picture to the left we see the socket itself, and the surface is perforated and has kind of a lattice structure. It's because of this lattice structure that the tissue inside the body ties better to this type of prosthesis than if it was a blank surface. And it's because of this that there's a huge potential in 3D printing parts for humans using metal 3D printing. With 3D printing, it's also possible to achieve some new thermal properties with materials that you weren't able to use before. So what is thermal when we're talking 3D printing? Well, it's a component's ability to absorb or give off heat. And if we look at the formula in the top right corner, it demonstrates pretty well that the amount of heat that can be transported depends on the size of the contact layer you have and how thick the walls are that need to transfer the heat. And if we look at the examples of 3D printing in the bottom, then we can see that 3D printing can make some pretty amazing geometries with some large surface areas. And that's why it's interesting to use 3D printing as a heat transferring source, either to cool or heat things. One of the places where we can utilize 3D printing to produce some thermal components is, for instance, a CPU cooler for computers. What you want from a CPU cooler is essentially that it's as efficient as possible, as small as possible, and weighs as little as possible. So if we look at a cross-section of a conventional cooler, It looks something like this, where we have some coolant coming in and some coolant coming out. EOS then looked at this and asked, how can we optimize this cooler? And they did that in 8 days, and they came up with this solution. Again, we have fluid coming in and fluid going out. But as we can see in the bottom, there's a large cavity with coolant all along the bottom plate that faces the CPU. And if we look at what came out of the printer, then it looks something like this. This one is printed in copper, which has very good heat transferring properties. And if we look at the results from this project, then in 8 days they actually managed to get on the same level as a high-end CPU cooler. And where they really managed to make an impact was in terms of weight. So we went from 407 grams to only 107 grams, and the volume has been reduced to a fifth. So you may think, how interesting is this? It's actually pretty interesting, because all this either goes inside our very small laptop, or it goes inside a huge server station where space is very costly. So the smaller, the better. The next case is an industry case that focused on whether we could produce headlights for cars with cooling for the LED bulbs. On top, we have the conventional part, and below we have the 3D printed version. And what's really interesting about this case is not only that we can optimize the cooling, but also that we can stack the parts in the build platform. This means that we can fit 384 parts in one build, and this shows that we're able to produce just as many with 3D printing as we could conventionally. So this is quite interesting. We took the design and looked at the thermal properties we needed, but we also optimized it for the 3D printing process. And actually, when it comes out of the printer, it's ready to have the LED mounted. Now it's time to look at how we get more functionality into our 3D printed parts. So what is functionality when we talk 3D printing? That is when we're able to get more functions into our parts than we were able to conventionally. For instance, as the Clever Pigeon says, it could be something that affected performance, something that affected how easy it is to service the process in which the component is part. For instance, does it help optimize the process? So we'll look at some different cases where we utilize the extra functionality that 3D printing gives us. The first case that we'll look at are flexible fingers for a robot gripper. The advantage of these grippers are that we can pick up things very gently, as we can see in the picture to the right, where we pick up an onion. Furthermore, as we can see below, it's possible to get in very narrow spots and pick up components without moving the gripper very much. If we look at how this is printed, then it's actually printed in one part with hinges built in so it's able to move, and it would have been very difficult to manufacture this conventionally. The next case we'll look at that utilizes the functionality of 3D printing is a spatula for folding dough. You may know the scenario from home where you're working with a spatula, and then when you flip dough over, the dough sticks to the spatula. Here, you've solved this issue by making holes in the spatula and then blow air in through the end so the dough will release much quicker. Since this spatula is for industrial use, it needs to happen very quickly, so there are a lot of holes and it's pressured air that's coming through. This case has actually reduced the amount of parts needed to make this spatula with 80% if you compare to conventional manufacturing. Plus, there are no weldings in the area that's in contact with the food. So this is a really good example of how you utilize 3D printing to add more functionality to a relatively simple part. The next case that we'll look at is one of the more advanced ones, and it's really gained some extra functionality from using 3D printing. These are pickups for record players that are produced by the company Autophone, which are world leading in this area. The special thing about these pickups is that they are 3D printed in metal using the powder bed fusion technology. And since we're using this technology, then we can make cavities with loose powder in it. And the interesting thing about that is that the loose powder has a dampening effect on the pickup, which means that you'll get a much more pure sound through your speakers. In fact, the sound is so pure that these pickups have been named the best in the world. Next up, we'll look at lattice structures. So if we look at what a lattice structure is, then it's a series of points that are arranged in a distinct pattern. And for the sizes that we're looking at here, it's only the 3D printing technology that can be used to make these solutions. As you can see in this figure, lattice structures can be elastic and bend in all different directions. And this is really interesting because we can use them for lightweight solutions or for functionality that weren't possible before. We'll illustrate that with a few cases. This case is one of the stranger ones, where Adidas has decided to make a running shoe that's harder to run in. So what they did was to design a lattice structure that actually absorbs energy, which makes it harder to run. Therefore, it'll feel like you're going for a run in the sand dunes when in fact you're only running on asphalt. You can see that Adidas has invested heavily in 3D printing when you visit their website. Here you see quite a few shoes with 3D printed soles, and they're all available on the market today. One of the places where lattice structures are also interesting is when we start to talk infill of our 3D printed components. If you have an FDM printer, you know all about them making honeycomb structures, so it's not necessary to print a massive part. This is mostly just to save material, and the part I have here is the crank box for a bicycle, because the bicycle industry has also started to look at 3D printing. Here you have some outer geometries that you want, and you have some inner geometries, and essentially you just want the parts to be as stiff as possible and as light as possible. And this is really interesting when we start to talk about metal printing, because here you can also print lattice structures that mainly have the function of stiffening the part. You cannot talk about 3D printing without also talking about lightweight. So why is lightweight interesting? Well, if we look at the financial perspective, then all the material that we add when printing adds a cost. So the more that we can reduce the mass of our part, the cheaper the part will get. And I guess that's something we're all interested in. Also, this often leads to us getting a lighter part than if we were to design and manufacture it conventionally. If we look at the formula in the top right corner, we can see that the energy needed to move a mass at a given speed is quite depending on the mass. So if we can reduce the mass, we need less energy to move it. If we apply this to a motorcycle like the one we see here, then this one has a topology optimized frame which is lighter than if you were to manufacture it conventionally. This then means that you need less fuel to move this motorcycle at the same speed. The first case that we'll look at here is a knife which is mounted on a robot in the food industry. And if we look at the original knife, then we can see that it consisted of 20 parts and weighed around 800 grams. 800 grams may not be a lot, but by optimizing it, we managed to get it down to 80 grams and consisting of just one part. By 3D printing the knife, we also get a shorter delivery time, and the production price is reduced by 60%. Furthermore, it's interesting to note that by reducing the mass of this knife, then we can increase the speed of the robot. This actually means that we can go from having 8 robots to only having 6 robots running the same amount of dough. One industry where weight means a lot is the bicycle industry, as we mentioned previously, because the lighter you can make your bike, the less energy you need to move it, say up a mountain. One example is from SRAM that looked at optimizing their bike crank arm. This has been designed so it doesn't need support material when being printed, and it's printed in titanium. By printing in titanium and by topology optimizing it, it's now twice as strong as a conventional bike crank arm, and it's 20% lighter. So this is really interesting that you can actually save this much weight in such a small component. One of the really interesting things when we're talking 3D printed parts is the design freedom that we get compared to conventional manufacturing. So what is design freedom? It means that we have some new limits of what is possible to manufacture, and that gives us some new possibilities that we didn't have previously. So if you have a brilliant idea in your head like the guy to the right, well, then there's actually a pretty big chance that it's possible to manufacture it. One area where the design freedom of 3D printing is interesting is in the food industry. Here it's the company Marel that makes machines for food processing. The example that I brought here is a robot gripper, and when you first look at it, it doesn't look as if it utilizes this design freedom. But then if you look closer, you can see that there are roundings practically everywhere, and that makes the part easier to clean. We can also see that the part is 50 centimeters long, so if we were to make it conventionally, then we would maybe need to mill it out. This would require a big block of plastic, so we would need to mill away a lot of material. You could also have it consisting of several different parts, but then you would have assemblies in a food contact area, and that's not ideal either. So 3D printing really is the best solution. Marel has really adopted 3D printing and the design freedom that comes with it. And here we can see a selection of all the robot grippers that they have designed for the 3D printing technology. This is a case that I really find interesting. Michelin saw the idea in using 3D printing for their injection molds for casting tires, since they could get some additional functions and better grip out of their tires by using these molds. In fact, they've been doing it since 2013, so they've been at it for a while. They also made a small 4-minute video where they explain why and how they use 3D printing, and you'll find a link for that at the end of this presentation. The last feature that we'll look at here is computer-aided design, because without a computer there wouldn't be anything called 3D printing. The most common way to construct and design a part is by designing it in a 3D CAD program. It could, for instance, be one of the programs that I've listed here. But since 3D printing allows you to print some very advanced geometries, we're starting to see more and more new programs where you can actually have the computer generate the design. We'll take a closer look at that in the next couple of slides. One of the tools that you can use on the computer to generate a design is topology optimization. Here, the computer calculates how much mass we can remove but still have the part last. This could look like the figure below, where it's optimized so you get some more natural shapes, kind of like bone structures or geometries from nature. With topology optimization, we looked at how much material we could remove from a part, but with generative design, we look at how we can connect different dots with the least amount of material. In this video, you can see an example of how it works. In my opinion, this is probably one of the coolest ways that you can design a robot gripper. This is a website where you add the part that you want to optimize, and then you check where you want the suction cups to be, and the software generates a robot gripper like you see in the picture to the right. When you're done, you just press order, and then they'll print it in SLS for you, and you get a robot gripper that perfectly fits the part that you need to handle. One of the biggest challenges when we're talking 3D printing is actually finding out which parts it makes sense to print and which it doesn't make sense to print. The company Caster has made a software to analyze your entire collection, and I'm sure this is something we'll see more of, where we get digital solutions to help you make the right choices about when to print and when not to print. Finally, here are some links for the different cases if you want to learn more about why it makes sense to 3D print them. Hi, my name is Ronnie, and in this module we'll look at a 10-step design guide for additive manufacturing. The agenda for this video is to first look at why we should design for additive manufacturing. Then we're going to go through a 10-step design guide to achieve the successful design, and finally we're going to round off with a few conclusions. So why should we design for additive manufacturing? Well, previously with subtractive manufacturing we used to remove material from a block, but now with additive manufacturing we have to add material in order to create something. So there's a shift in the mindset from removing material to adding material. When moving from subtractive to additive manufacturing, we get the most out of the technology if we actually design for it. In this pyramid, we can see some of the different ways that we can use additive manufacturing. And ideally, we want to be on top of the pyramid where we utilize additive manufacturing to create new products. If we look at some of the benefits that we achieve by moving to the top of the pyramid and design new products, We can see that there's a whole range of them. We need less support material, we get a better surface quality, we get a lower price, shorter print times, better tolerances, and we're able to fit more parts on a platform. In addition, we get a range of design benefits, as we can see here. For instance, we can build lattice structures, we can make lightweight products, and we can take advantage of part consolidation. Now we're ready to start designing, and to best illustrate how you design for additive manufacturing, I've brought a case. Here we need to redesign a robot gripper for additive manufacturing. For this product we have a clearly defined requirement specification, and we also have some goals that we want to achieve. For instance, we want to make it lighter than 1300 grams, and we want it to consist of significantly fewer parts than the 72 we see here. So which of the design benefits that we saw before can we actually utilize when redesigning a robot gripper? Well, first of all, we can make it lighter, then we can make part consolidation so we end up with fewer parts in total, and we can integrate the air tubes for the suction cup into the gripper itself. So to go from the original gripper to a 3D printed gripper, we need to go through 10 design steps. First, we need to choose the material that we want to print in. We have to choose the technology that we want to use. Then we have to define the contact areas and define the print orientation. Then we have to connect the contact areas and add the support structure. Then we have to look at the cross-section area and pay attention to the different design rules. Then we have to validate the design, and finally we are ready to print. The first thing we need to do is to see if the material that we want to produce the gripper in is actually available. One place to start is this Zenvol database that lists all the different materials that you're able to print in, paired with the printers that you can actually print these materials on. I've decided that we want to print this gripper in aluminium since it has a good strength and it's lightweight. The next step is to choose the printing technology that we want to use. This overview is a good place to start, and below you can see the different materials that the technologies are able to print in. I've listed the ones that could be interesting for manufacturing a robot gripper, and the one marked in green is the one I decided on. When looking at the technologies, we need to clarify what the build volume of this technology is it sufficient, and do we need support material or not? What kind of post-processing is needed? What are the tolerances and could they be a challenge? What is the surface quality, and do we have any demands for surface quality? And finally, how can we quality assure our gripper? We've decided on the SLM technology, and I'm fortunate enough to have an SLM 280 metal 3D printer available. That's the one that you can see in the upper right corner on the picture. Below you can see the volume of the build chamber, and to the left you can see that there's different layer thicknesses available, which defines the quality that you get out of the printer. The standard is a 60 micron layer thickness. In addition, we can see that it uses two 700 watt lasers, which also affects the quality, but also the speed with which you can print. Now that we've selected the printer, we have to look at the contact areas. Basically, it's about connecting A to B in the easiest possible way, and usually there are some obstacles that you need to get around, here illustrated by the two stars. If we apply this to the robot gripper, we see the gripper here, and here we see the contact areas. We have the suction cups, then we have the mounting bolts to mount it on the robot, and finally we have a fitting for the pneumatic connection. So these are the contact areas that we need to connect in order to make a robot gripper. Now that we've defined the contact areas, we need to look at the print orientation. The orientation is very important, both because it gives some benefits if you have a good orientation, and it impacts your design. When talking about orientation, the vertical direction, also known as the Z direction, is the most important. Some of the benefits of a good orientation could be that you reduce the need for support material, you improve the surface quality, and you get a shorter print time. If we apply the orientation to the robot gripper, then to the right we can see that I've defined the Z direction as the direction which the gripper is actually mounted on the robot. I've done this because I believe it will give us the most symmetrical robot gripper, but that might change in the design phase where you learn something different through design iterations where a different orientation may make sense. But as a starting point, I want to use this orientation as the basis for my design. The first thing to do after defining the orientation is to draw different sketches of how you can connect the different contact areas. The blue lines show where we need some air flowing through tubes and also where we need some strength in order to lift the box that will actually be lifting with this robot gripper. In addition, we have the red lines, which is where I want to connect the gripper to the robot itself. Here we've made a sketch of the connection between the different contact areas, and now we can start to add some volume to these areas. It could look something like the drawing we see here, with round tubes connecting the contact areas. And we could actually just print it like this. But since we're printing with the SLM technology, we have to account for support material. So it could be interesting to see whether or not we could reduce the amount of support material. That is because it gives some significant benefits to reduce the support material. For instance, you reduce the print time, you reduce the support removal time, you reduce the amount of grinding needed to remove support marks, and in turn you get a better surface quality. One way to reduce the amount of support material is to optimize the angles so that they're all above 45 degrees in relation to the build platform. Another possibility is to reduce the build height and thereby also reduce the need for support material. You can optimize the shape of the channels so you don't need support inside the channels. And finally, you could build support as part of your part, as we see in the picture in the bottom right. If we look at support material for the robot gripper, I've added it to a preparation program where I've auto-generated the support to see where the support is and how much there is. If we start with figure A, this is the orientation I took as my starting point. And here we can see that there is some support material, so maybe it would be possible to reduce this. In figure B, I've turned the gripper upside down, and we can see that there's almost the same amount of support as in figure A. And in figure C, I've tried placing it vertically because that way we could have more grippers on one platform. So this could be an option if we wanted to series produce it. But I've decided to move forward with figure A because I think that gives us the best orientation. Now we'll look at the robot gripper again and see how we can optimize it using some of the guidelines that we saw earlier. One way was to reduce the height and thereby reduce the amount of support needed. We've tried doing that here, where we have reduced the height from 92 millimeters to 49 millimeters. And as we can see, this reduces the amount of support with nearly 50%. The next thing we need to look at is the shape of the channels where air will be flowing through. Our channels are designed with a diameter of 10 millimeters, and here we can see that it's not possible to design round channels with a diameter of above 8 millimeters without using support inside the channels. So instead, we need to choose one of the other 4 options for shaping our channels. So we can make it ellipse-shaped, droplet-shaped, diamond-shaped, or shaped like a house. And these are the 4 options we have for shaping our channels if we want to avoid support inside the channels. As we can see to the right, we can also combine these different geometries when designing the channels for 3D printing. I've decided to move forward with the figure that we see in the bottom left corner, where we combine the round geometry with the diamond-shaped geometry. Now we take this knowledge about channel design and apply it to our robot gripper. And then we end up with a design that could look something like this. Here we have the round holes in the vertical direction, and we have the diamond-shaped channels in the horizontal direction. Next, we need to look at how we can optimize the cross-section area of the printed part, since this has a huge impact on the quality that we end up with. Here's an example of a large block where we've defined a C direction. That means that we'll print a lot to begin with, but we'll also have some big leaps in the printing process in terms of how much we'll be printing in each layer. There's different ways of solving this issue of making the part more printable by optimizing the cross-section area. One way could be to orient the part differently. That way, as we can see in the graph, we get less that we need to print in each layer, and we get a more even increase in the amount that we need to print. That in turn gives us a better quality of the printed part. So the orientation definitely has something to say. Another way to optimize the cross-section area could be to add chamfers or roundings to our part. This doesn't really cost extra to print, but it significantly improves the quality of the printed part. A final way to optimize the cross-section area could be to hollow out the part and maybe, as we see here, add a honeycomb structure inside. This would also give us a lower volume to print in each layer and in turn give us a better quality of the final printed part. Let's make a quick analysis of how this looks for the robot gripper. If we look at the graph to the left, we can see where we have changes in cross-section area where we start printing more, and at the red arrow is where we potentially could have a challenge. If we then look at the picture to the right, we can see that the yellow lines indicate that there's a change in the cross-section area, and that's because we start printing the attachments. So here it's a good idea to have some roundings here below in order to allow for a smoother transition in the amount that is printed. In addition, we can see that the big changes are when we go from printing something to not printing anything. So we're not too worried about that. And we're not too worried about the green arrow either, since we're decreasing the amount that we're printing. It's more when we're increasing the amount that it could be a challenge. But the way the design of the gripper is looking now, I don't see any challenges in printing it. Now it's time to look at whether the robot gripper complies with the general design guidelines for the technology that we have chosen. For this, Hubs is a big help. They offer the 3D printing handbook, which is a great help when designing for additive manufacturing. But in addition, the table that you see to the left is very helpful. Here you have the overall measures and limitations that you need to stay within in order to get a successful print. If we proceed with the bottom one, which is for the SLM technology, which is the one that we're using on the robot gripper, we can see that there are some general measures and limitations that we need to stay within to ensure that we get a successful print. Here I have listed the ones that I find particularly interesting for the robot gripper, and these are the ones that I want to pay close attention to. We need to check that we don't have any wall thicknesses that are below 0.4 millimeters, and our smallest wall thickness is about 1 millimeter, so here we are quite safe. We already looked at support and overhangs, where we designed our channels so they didn't have overhangs that were outside the guidelines that we see here. The smallest holes that we have on the gripper is for the mounting bolts, and they have a diameter of 6.5 millimeters, so that's also well beyond the limit of 1.5 millimeters, so that shouldn't be a problem either. And the escape holes where we need to get our powder out have a diameter of 10 millimeters, so that's not a problem either. And finally, we can easily live with the tolerances of plus minus 0.1 millimeter. Consequently, we can see that the robot gripper complies with the general design guidelines for SLM. The final step before we start printing is to validate our design. We can check that the robot gripper actually fits on the robot, and we can do that in our CAD program. We can also use simulation tools to simulate if the robot gripper is strong enough and if it's possible to optimize it even more. If we look at the robot gripper, I've made an FEA simulation where I used a safety factor of 1.5. Here we get a maximum stress of 88 for the robot gripper, which is well beyond the yield stress. We also looked at the displacement when lifting a box of 4 kilos, which this gripper will do. And the maximum displacement was 0.3 millimeters, which is acceptable for a gripper of this type. This indicates that we could optimize our design even more, maybe by reducing the wall thicknesses of our channels from 1 millimeter to 0.4 millimeters. Now we're ready to start printing. We've managed the design phase. Now we need to convert our file to a printable file format. Then we need to add it to a preparation program where we orient our part the way we designed for. Then we add the support and we slice the build job into several layers, which we can then print. Then we start printing, and afterwards we remove the support and take the part through the necessary post-processing steps in order to get a nice surface finish. What we achieved with this case is that we reduced the number of parts from 72 to only 6 parts. We reduced the weight from 1300 grams to only 150 grams, which is a very big reduction. And finally, we integrated the external air tubes into the gripper itself. In the picture to the right, we can see what the gripper would look like when it's mounted on a universal robot. To sum up on design for additive manufacturing, this new manufacturing technology has given us a lot of new design possibilities that we can apply to our parts. Of course, there are also some restrictions for the different technologies that we should pay attention to. So the goal is to end up down here in the area of design freedom, where we utilize all the different design possibilities, but at the same time pay attention to the restrictions, so we end up with a great design for additive manufacturing. Finally, what we want to achieve when designing for additive manufacturing is to design some great parts that are also great when they come out of the 3D printer in the end.
Hello, my name is Jeppe. In this module, we'll have a look at whether or not additive manufacturing is a sustainable production method. So the first obvious question is 3D printing actually a sustainable production technology? The right answer is maybe. Another answer could be it can be, it depends. Compared to what? I can only say that there's a lot of clever people having looked into this. There's been written books about it. There is organizations about it and many opinions. Anytime you manufacture something, it's not as such sustainable, but this is definitely an enabler for sustainable production. And I will give you some details on that. More things we can say about is 3D printing a sustainable production technology is that there has been written a lot of articles. I have brought a few of them here, a few of the frameworks that you typically use to assess the sustainability of production methods and of the sustainability of 3D printing. I don't want to go into details, but I have the references here, so you can look into the details yourself if you want further information. I can also only say that there's a lot of people claiming that 3D printing helps these sustainable development goals from the United Nations in a number of different ways. Again, I don't want to go into details, but I will come with some examples of how 3D printing is used as a sustainable production technology. One of the frameworks that I actually do like is this one from the article that I have stated here, stating some of the drivers for AM sustainability. You have a number of different enablers, as I will call them, because as such it is not a green sustainable technology, but it enables some of these features. For instance, weight savings. You can make lighter parts. Improved product efficiency. For instance, oil coolers, heat exchangers with a higher performance, with a lower energy consumption. Part consolidation. So where you previously had maybe 20 parts, you collect that into one part and thus gain some benefits. Make-to-order manufacturing and mass customization, making individual parts for the individual customer on demand. And the final point in this graph here, production of spare parts and repairing. Instead of completely replacing a really expensive and difficult to manufacture component like a gas turbine burner, you can just repair it using additive manufacturing, obviously gaining some sustainability advantages. I do believe though there are some features missing on this, so I added a few ones myself. Some of the non-technical and process related benefits that include a novel supply chain. So as we see in the figure in the lower left, you can go from idea to a part made at the customer in one step, where you would typically have a number of steps involving prototyping, production, assembly, distribution, storage, retail, before it actually comes to the customer. So it's a new kind of supply chain. You can also see you get the ability to make local production, so you actually print it at the customer or near the customer, thus enabling a reduced transport. You can reuse the material. It's a highly efficient, energy efficient and material efficient process because you only use the material going into the product. Finally, you can have files in stock and not products. And this is a really big issue today because you need to have spare parts for all your equipment to be able to service it really quickly. but some of the features that we are looking into is having files on stock instead of products. Now I have a number of examples showing how others have used additive manufacturing and 3D printing to enable a more sustainable production of the parts. One of the really traditional cases I have here, it's from a European project where they optimized some aeronautics components. And we all know this belt bucket from an airplane. The traditional one weighed about 155 grams. Using AM and optimization, it could be reduced to 70 grams. There is a large number of these on a plane, and if you multiply with that and you see how much fuel is actually used per kilo, you can see that over the airplane's lifetime you save 3.3 million liters of fuel. So that is one of the reasons why the automotive and the aeronautics industry has really adopted additive manufacturing, because you can make these lighter components, thus saving a lot of energy, a lot of fuel, and a lot of money. The next example that I have with you is a case that we did at DTI a number of years ago, together with the Boeing company. It's a bracket. It's a piece sitting between the chassis and the motor block, so a rather flight critical part, where we showed that we could print this, and it was in compliance with this standard ASTM F2924, and it had a number of benefits regarding sustainability, because they looked into scenarios where they could quickly repair their flights, they could make the parts lighter, they could have files in stock, as I mentioned, instead of the physical parts. So they were looking at redesigning their supply chain actually. And we showed that this was possible with the current technologies. We also showed that you could use this phenomenon called topology optimization, where you simulate the part and the forces on the part, and through an iterative simulation process you remove all of the material that is not needed. In this case, we could make it stiffer, we could make the displacement smaller, and we could reduce the total mass by 35%, from more than 300 grams down to about 200 grams. The next example, also from the aeronautics industry, because there are so many examples from there, is a really classic one also, the GE fuel nozzle that they use in their LEAP engine. It's a really famous case because it has so many benefits. So as we can see, they could reduce the inventory by 95%, make a 30% cost efficiency improvement, 25% weight reduction, do part consolidation, so it went from 20 parts down to 1 part, and make it 5 times more durable. All in all, reducing a vast amount of fuel related to a vast amount of money for them. So they are producing several hundred thousands of these parts. The next example is a case that we did at DTI in collaboration with Aarhus University and a company called Thyoma Tools. Thyoma Tools are making these cutting tools. You can see the traditional one here, weighing about 6 kilos. Again, doing topology optimization, so saying what are the forces and removing all the unnecessary material. We went with a design like this, weighing about 1.5 kilo. So again, we could reduce the weight quite a lot, and it's important because it's used in places where it's difficult to go, for instance on oil rigs or offshore wind farms. And it's really important to have the parts as light as possible. Furthermore, when we're talking additive manufacturing, the less material you have, the cheaper it gets, and the faster it is to print. So all in all, very beneficial. To give you an example where it's not in the aeronautics industry or in the tooling industry, we have one here from consumer goods. It's a rather new case where this company called Mauer is making these glasses, and together with EOS and the Fraunhofer Institute, they have documented that it is much more sustainable if you do the production with additive manufacturing. I've added a few links so you can see some of the news and some of the numbers behind it. But I like this example because it also illustrates that it is for all types of products, including these consumer goods. The final example that I have here is in relation to thermal applications, because there's so much potential within additive manufacturing enabling thermally optimized parts. Some of the examples we can see here, it's like heat exchangers, heat sinks, where these very advanced structures enabled by additive manufacturing enables more energy efficient products. At DTI, we have a project called ECE, where we look at thermal topology optimization with these partners. And in this way, you can make the absolutely most topology thermally optimized parts, saving a lot of energy. So I really do believe this is the future for thermally optimized parts. Final slide, just want to round off by naming some of these drivers for AM sustainability. Why is 3D printing an enabler for sustainable production? Because I believe it all boils down to that. 3D printing enables more energy efficient parts, production of lightweight parts. It enables local and distributed production. It provides the ultimate flexibility in your production. It yields a short time to market. It can reduce overproduction. It yields material savings. It can reduce the scrap. And all in all of these things enable AM to be a more sustainable production method.
Hi, my name is Henning, and in this video we will talk about the economy of 3D print. We will initially go through traditional cost calculation, then we will look at the business case evaluation, and finally we will give an example of what we have been through. First, we look at traditional cost calculation. When you have to choose between different manufacturing methods, you often make a cost calculation to judge between the alternatives you have. Here we show an example of a comparison where we on the top have the calculation for traditional manufacturing with all the cost contributions, and at the bottom we similarly have a calculation for additive manufacturing where the cost elements are highlighted with green. Here we see a typical picture of traditional manufacturing versus additive manufacturing. The dotted line shows the traditional manufacturing where you have high initial costs, while for the additive manufacturing you have lower initial costs and approximately the same cost per part no matter how many you produce. For the traditional manufacturing you have to depreciate the high initial cost over the number you produce. And then at a number of X you have break even, meaning that with a number lower than X, you would probably choose additive manufacturing, while for a number higher than X, you would choose traditional manufacturing. However, this method only gives you a limited picture of the situation when you consider to use additive manufacturing. Conventional cost calculation and comparison of 3D printing and traditional manufacturing shows only a limited picture and often not in favor of 3D printing. Why is it then that people choose to produce using additive manufacturing? To set up a correct business case, you need to look at more than just the costs and savings. And that is what we are going to look at here. So in addition to costs and savings, you need to take into account the added value. To be a bit more specific, we here show some examples of what the cost contributions may be and what the added value elements may be. To the left you see the cost contributions, the well-known ones from normal calculations, and to the right examples of added value. It may be new features for functions, it may be a shorter delivery time, shorter time to market. It may be individual adaptation of a part to human beings, or you may open up new markets, for instance, or your maintenance cost may be reduced because you have 3D printed a part. But the essence is how much is it worth to put money on each contribution. This graph shows a way of illustrating the different contributions for added value. As you see, the arrows point both upwards and downwards. The upward pointing arrows indicate a positive effect, and the downward pointing arrows indicate a negative or an extra cost by introducing a 3D print. At the end, you have to sum up all contributions. If the sum arrow points upwards, it is a positive effect by introducing 3D print, and it may indicate that that's the way to go, while if it points downwards, a sum arrow that shows an extra cost, it's probably not a good idea to go to additive manufacturing. On this slide, we specify some situations where 3D print may add value. Not always, but it may. As number one, if you have designed a part in such a way that it's the only option to produce using 3D print, that's obvious. Then if traditional fabrication is expensive or with high complexity, it may also be worth considering 3D print. The batch size is limited. We are not talking millions of parts. We are talking tens, hundreds or thousands or even tens of thousands of parts with the present level of 3D print technology. If you by traditional fabrication have large material waste, it may be worth considering 3D print. If it makes sense to consolidate parts, integrate them into one piece, it may make sense. If you are able to reduce your operating cost by smart design, that is 3D printed, it may make sense. If you have frequent design changes and want to go to the market but are not sure you have finished your design, it may make sense to start with additive manufacturing. If you have high storage costs and can produce on demand, it may make sense. If you have long delivery time and the breakdown of your equipment is expensive, you can make a quick fix using 3D print. You can customize parts knowing that producing one part costs you approximately the same as producing several parts per part, and you can personalize, adapt things to individuals using 3D print. Finally, we have an example where we illustrate what we have just been through. The example shows a flight buckle for a safety belt. To the left you have a traditional buckle, and to the right you have a buckle optimized for additive manufacturing. The challenge is to reduce the carbon footprint by using 3D print. And how is that done? The solution is to optimize the design for 3D print and print it in titanium alloy. What was gained by that? Well, the result was a weight reduction of 55% from 155 grams to 70 grams. That's not much, you can say, but for an Airbus 380 with 853 seats, it sums up to a total weight reduction of 73.5 kilo. And it has been calculated that over an airplane's lifetime, each kilo contributes to a fuel consumption of 45,000 liters. For the 853 seats, that means then that the 73.5 kilo weight reduction reduced the fuel consumption with 3.3 million liters, corresponding to a saving of 2 million pounds over the airplane's lifetime. In addition to that, you have improved strength and you have simpler scrapping or recycling at the end. So we go from several materials to just one. So that's a simpler recycling. A way to illustrate this is to make a list of where you have impact by changing to additive manufacturing. And the arrows illustrate the positive and negative impact you have, where the green upward pointing arrows show a positive effect and the negative effect is illustrated by downward pointing black arrows. And the overall positive effect is shown by the big green arrow for the operating cost, meaning the fuel savings. A way to illustrate this is the graph to the right, where you have the different contributions, downward pointing and upward pointing arrows, summing up to a big positive effect to the right, indicating the big fuel save by this change to additive manufacturing. Putting figures on this, at the top we have the fabrication costs, and the conventional buckle sums up to about 10,000 British pounds for the full aircraft, and using additive manufacturing we first have to invest in the R&D work, which is quite costly, namely almost 1.5 million British pound, and on top of that the fabrication cost or manufacturing cost for the titanium buckle is 165,000 British pounds, meaning almost 17 times higher than the traditional buckle, and together we get an extra cost for the first plane for 1.6 million British pounds. Why is it then that it makes sense to go to additive manufacturing? That we see at the bottom for the added value, because you have the big fuel saving of 2 million British pound per plane. That gives us a saving for the first aircraft of almost 400,000 British pounds, while for the following aircraft you have a saving for each of them of 1,845,000 British pounds. On top of that, you have some benefits that are more difficult to quantify economically, namely you have an improved strength of the buckle, and it's easier to scrap and recycle. So, summing up at the bottom, the total impact for the first aircraft is the benefits and a sum of almost 400,000 British pounds, while for each of the following flights you have the benefits plus 1,845,000 British pounds by changing to additive manufacturing.